So next we're going to take a close look at probably one of the most important results of this section, and that is the local extremum theorem. So let me write that on the board. So local extremum theorem. The local extremum theorem basically says that whenever you have an interior point, so in other words a point inside the domain that's not on the boundary, aka it's not on the endpoints of the domain. So for any interior point, if it's a local extremum, then it must occur at a critical point. So we can write this as follows. So if an interior point x equals to a of a function's, so I have a function f's domain. So we are at an interior point of the domain. So if an interior point is a local extremum of the function f, then it must be a critical point. So in other words, when we set aside boundary points or endpoints of the domain for separate consideration, when we only look at the interior of the domain, whenever you have a local extremum, it must be a critical point. So in other words, local extrema only occur at the critical points on the inside of the domain. So we can also say this is equivalent to local extrema only occur at critical points and possibly at boundary points, right? Because this theorem excludes the boundary. It just, so for example, if you have a domain that's a closed interval from 0 to 1, this says that on the open interval 0 to 1, any local extremum aside from the actual extrema at the points 0 and 1 themselves, so any local extremum that is strictly greater than 0 and strictly less than 1, in other words, any extremum in between must occur at a critical point. Now, it's important to note that to follow the logical implication. So local extremum for an interior point, so not on the boundary points, implies it's a critical point. That's what the theorem says, that if you have a local extremum, then it must be a critical point. Alternatively, every local extremum has to occur at a critical point, or every local extremum on the inside of the domain, in the interior of the domain, must occur at a critical point. And if we extend this to also those two boundary points, 0 and 1, we can say that local extrema only occur at critical points or boundary points. So that covers all possible cases for the local extrema. Now, what this does not say is it does not say that if a point is a critical point, then it must be a local extremum. So the opposite direction of this logical statement is false, and the opposite direction is called the converse. So the converse statement would be that if you have a critical point, then it must be a local extremum. That statement is false. A critical point may be a local extremum, but it may not be a local extremum. So basically this says that the extrema can only occur at critical points or boundary points, but just because you're at a critical point doesn't necessarily make it a local extremum. So I'll give you an example of why that would fail to be. So let's consider the graph of f of x is equal to x cubed. Now let's examine the point x is equal to 0. So let's look at x is equal to 0. So this is the quintessential counterexample to the converse of the local extremum theorem. So in other words, this is the main quintessential or main example that shows that the opposite of the local extremum theorem fails. And the opposite being that if you have a critical point, it must be a local min or a local max. Here we'll show that there is a critical point at the origin that's neither a local min nor a local max. So let's first show that the origin is indeed a critical point. So to do that, we just take the derivative. So f prime of x is equal to 3x squared. And remember, a local or a critical point is a point in which either the derivative is not defined or the derivative is equal to 0. So at the origin, so at the point x is equal to 0 in particular, the derivative is equal to 0. So this implies that x equals 0 is a critical point. Right? Take the derivative, set it equal to 0. If the solution x equals 0 does return a 0 value, so the derivative is 0, meaning that the tangent line to the graph is horizontal. And maybe I can draw a slightly better graph to make that more pronounced. Okay, so basically x cubed, it comes like this, and it just has, for one moment, it has a horizontal tangent line only at x is equal to 0. So it's coming up, it levels off with a horizontal tangent line for that one moment, and then it keeps increasing. So it's increasing, stops, and then it continues to increase. Right? So it's not a minimum, because if I look a little bit to the right of that point, no matter, I can find a greater value. In fact, any open neighborhood around 0, it passes through 0 with a horizontal tangent. But no matter how small you shrink the interval, there's always greater values on that open interval than 0. And there's always smaller values than 0 on that open interval, no matter how tightly you squeeze that interval down. So it's neither a local minimum nor a local maximum. And yet we have a critical point. So if you have a critical point, it could be one of these cases where the function's increasing, it levels off, and it keeps increasing. It's not a minimum, it's not a maximum. Okay, so critical point by itself does not mean that you have a local extremum. What the local extremum theorem says is that whenever you do have a local extremum, it is at a critical point or a boundary point. So, in other words, the only places where it's even possible to get a local extremum are the critical points. You might have critical points that are not local extrema, but as long as you check all of your local extrema, or all of your critical points, you'll capture all of the local extremum, except possibly at the endpoints of the domain. So let's take a look at just another example. Okay, and I'm going to draw just a random sketch of a graph. So let's say that we have an endpoint. Cusp, like that. So notice we have a sharp, jagged edge there. So the critical points are going to be right here, because we have a horizontal tangent line. Right here, because we have another horizontal tangent line. Right here, because again we have this horizontal tangent line. Right here, because the derivative is undefined. We have this jagged edge, so the derivative is not defined at that point, so that's also a critical point. So 1, 2, 3, 4 critical points. Now the local minima, so we have, oh, we already used red. Let's use this one. So this point, and that point. So those are our 3 local minima. Right, because at this boundary point, that output value is less than any of the output values nearby that are still on the domain. The same is true down here. This fails to be a local minimum because immediately to the left of that point there are smaller output values. And this is a local minimum because immediately to the left of that point it's greater And so all the neighboring points are greater than the output value right there. So we have 3 local minima. The local maxima are here and here. So those are the local maxima. So notice we have 2 local maxima and 3 local minima, 4 critical points and 2 boundary points. So we do have this one critical point right here. It's a critical point, but neither a min nor a max. So sometimes that's called a saddle. Saddle point. So a saddle point is basically, this isn't used too much in Calculus 1, but the saddle point is a term for a critical point that's neither a minimum nor a maximum. It really comes into play in Calculus 3 when we have graphs of functions of 2 variables. So we have sort of these 3-dimensional graphs that look like this. Right, so it looks kind of like a saddle. And so at this point, if you go this way, you can go up, but if you go that way, you can go down. But it is a critical point because in this case, the tangent plane, so we have a whole tangent plane instead of a tangent line, is horizontal. But if you go this way, you're going down. If you go that way, you're going up. You don't need to know that for now, but this sort of feature has a shape of like a horse saddle. So that's why this is sometimes called a saddle point. I only mention this because in this one-dimensional drawing, you might not see why they call it a saddle point. But that's known as a saddle point. Not too common of a notation terminology for Calc 1, but there it is. That is the local extremum theorem, which basically says that when you're on the interior points of your domain, aka when you exclude the boundary points, critical or local extrema may only occur at critical points. So the critical points are the only candidates for where you can have a local extremum. So this is a very important theorem. We'll bring this together with a more global picture and with an actual strategy for locating the global maxima and minima when we talk about the extreme value theorem, which is next. And also we'll also talk about strategies for locating these sorts of things. But right now, if you're just looking for local extrema, the consequence of this theorem is that you only have to check the boundary points and the critical points. So a corollary of the theorem, so all local extrema for a function must occur at the critical points and or boundary points. So in other words, if you have a local extremum, it must be either at a critical point or a boundary point / endpoint, whichever terminology you want to use. So the boundary points, aka the endpoints, are always possible places to have a local extremum, and the critical points are the other possible places for a local extremum. So outside of critical points and endpoints, you cannot have local extrema.